Okay, good morning. Today we are going to discuss almost the last chapter, digital data transmission. And the next class we are going to discuss encoding technique and error detection. Then the next time will be error correction. So that's all. This class is relatively easy compared to what we discussed before. So there are a lot of facts, not too many theories. Data communication systems, we need to know the source. The source, which is the input to the digital system. Basically, we have two types of input. The first one is the sequence of digits from computer systems. For example, you print something from computer to the printer. And usually, binary digits are the most popular. Sometimes n-ary digits are also used, but that is very rare. One concept is called a multiplexer. The communication channel is time shared by several messages simultaneously using a process of interleaving. For example, you just transmit at the same time, theoretically not at the same time, several channels from the same people. Lienholder, to code the digit into electrical pulses or waveforms. For example, if you want to transmit 1101, how are you going to transmit that? One option we know before is 1. For example, we use 5 volts to represent 1. So 1, 5, 5, 0, 1. Right? So that is only one of the options. The other option is, for example, we can use ASK. 1 means we have a sinusoid function. 0 means we have nothing. We already know this in the labs. So that is also an option. But anyway, in this class we are going to discuss a lot of line coders. And in the third lab, you are going to examine all this in details in the labs. We have on and off, that is very typical, we learned before. And the polar, bipolar code, and classified as return to 0 or non-return to 0. If the communication link is very long, then in between we need a regenerative repeater. That means in between we need to have some device. We receive the signal, then reshape it, amplify it, then resend to detect the incoming code and regenerate new clean pulses, then transmit again. Multiplexing, basically we have 3 types. The first one is called time division multiplexing. That means data are transmitted in frames in time. In each frame, sample of multiple sources, one by one, will be coded into PCM code. We are going to use the example in the next slide to show how we do this. The second type is called frequency division multiplexing. And the last slide is called wavelength division. And we know frequency and wavelength are related. Frequency times wavelength equals the speed of light. So that two actually is the same thing. The only difference is wavelength usually refer to very high frequency. For example, optical communications. In that case, the frequency is even in the terahertz. It's very high. Then instead of frequency, we use wavelength. Otherwise, they are almost the same. Frequency division means several narrowband analog signals can be transmitted by a single wideband channel, and digital and analog conversion is needed for digital transmission. Right, so this is the very simple example of time division multiplexing. For example, we have channel 1 and channel 2. Channel 1 wants to transmit 011, 010, and channel 2 wants to transmit 1011, 10. How we do this in time division multiplexing? Right? So this is one frame, right? In each the combine of the 2 channels, in each frame, in the first half, we are going to transmit channel, in this example, we are going to transmit channel 1, right? Transmit 0. Instead of the whole frame, we are only using half of it to transmit channel 1. Then the second half will transmit the channel 2. So you can see 0 here and 1 is from here. So in this frame we transmit 2 channels. Each channel use only, in this example, use only half of the time. And for the second frame, this one here, the whole frame will transmit both channels. And the first part is no, this one here. Okay, the first one is 1 here, the second one is 0 here. And similarly for this one, 1 and 1 here, and 0 here, and 1 here, and so on. In this example, we have only 2 channels, so each channel only occupies half of the whole frame. If we have 4, then each one occupies a quarter of it. So we can get the ideas from this simple example. Any questions on this? The advantage for this one is we can boost the efficiency. That means we use the same channel to transmit multiple channels, multiple signals. The cost is we are going to use a higher line speed. This one is a more practical example, time division multiplexing. We can see here, we start from the very beginning. We have analog signals, and the frequency is from 0 to 4K. What kind of signal is this? Anyone? Have a guess? What kind of signal is this? Analog signal. And frequency is from 0 to 4K. Right? That is our voice. Right? That is the traditional landline telephone system. Although the human voice can be from 0, greater than 0 to 20K, but most of the component is between 0 and 4K. Or high frequencies, the power is very small. So from 0 to 4K, and we use an anti-aliasing filter. What kind of filter is this? Low pass, band pass, high pass. What kind of filter is this? High pass? No, we do not want to use high frequency. Low pass or maybe better band pass filter. Then we use the sample and hold. That's the DA process. Then we get the PAM signal. Then we use the analog to digital converter. What is this process? PCM? Yes or no? This process is PCM, right? And convert analog to digital. And then PCM code, the output will be parallel, but we want to transmit in a series, so we need to use a parallel to series converter, and we get only one like this. So that is the first channel. Right? The second channel, same thing here, all copies here, and we have guess the second channel. And these two use a time division multiplier, and we combine together. For this one, the line speed is 64. Why it is 64? Anyone can figure out why it's 64 kb per second? Okay, 8-bit, right? And the frequency in each second, how many samples do we need? 8K, right? It's double the highest frequency, which is 4K. So 8K times 8 equals 64 kb per second. So that's the line speed of this one. Everybody should figure out this easily. Right? And this one is also 64 bit, 8-bit. Then we combine together. We are going to have 128. 64 plus 64 equals 128 bit per kilobit per second. Right? So this is the time division multiplier. Any questions? In real life, we may have much more than this, only 2. Right? We have like several hundred pairs of code can be transmitted. The next one is frequency division. The idea is the same, but this division multiplexing is applied in frequency. Right? So first one, channel. This channel is the frequency is from 300 to 3100. What signal is this? Again, it's the voice, right? It's like a call. So this one. And this channel 2, channel 3, and we maybe have a channel. Okay, we have only 3 channels here. All these 3 channels occupy the same bandwidth from 300 to 3100. Can we just add up this together? Based on our experience, we cannot, because if we add them together, all this will be occupy the same frequency band, then later time we cannot separate them. Right? So what we do is we shift this frequency to somewhere, and we shift another channel to a little bit higher frequency, and the third one to even higher. So the first one is between 60 to 64. We have some gaps in between. The second channel is 64 to 68. The third channel is 68 to 72. What technique should we use to do from here to here? How are you going to do this? Move this to here. You shift the frequency from low to high. Multiply, right? So technically we call that modulation. What kind of modulation? AM modulation. Right? AM modulation in time is just multiply. In frequency is just a frequency shift. Alright, now we have these three channels occupy different band, but then we can add up together. So this one is 60 to 64, 64 to 68, and this one here. Alright? Then we transmit this. And to the receiver, once we receive this one, what we are going to do? Okay, we use filter, band pass filter. Okay, we get this one, we get this one, we get this one separately. Then for each one, what's the next one? What's next step? We cannot hear this kind of signal, right? Because this is in a very high frequency. It's beyond our ear. Our ear can only listen up to 20K. This one is 72K. So what to do next?
Use a low pass filter.
Low pass filter. Does low pass filter work? Okay, no, low pass filter. If it's beyond this bandwidth, then we get nothing. So we cannot use low pass filter. We want the information here, but we do not want this high frequency. We want the information to be like this. What technique should we use? If I let you fill the blank, what we should use this to implement this. What is it? No one knows?
And you say you don't want the high frequency, right?
Right. This one we cannot hear this. Right? We hear nothing. What we want is the baseband information.
And you say you don't, at least after you use the band pass filter?
For example, okay, the radio send you 95.3 megahertz signal. You cannot directly listen to that signal.
And you say demodulation, that's what you're saying?
Okay, that's what we are talking about, demodulation process. We use demodulation process to bring this high frequency back to the low frequency, so we get the original baseband information. Alright, now this one is a more practical example here. Channel from 0 to 5, again voice, this channel 2, channel 3, and we have another channel 4 here. And this one is AM, right? That is the multiplier. And multiplier, once we have the center frequency equals 100K. What is the bandwidth for here? Right? You already know that. Okay, it's 95 to 105, right? Does it make sense? From this center plus minus B, right? Okay, so 95 to 105. So this is called a double sideband suppressed carrier. And we already know that we have two exact copies of this signal, so not necessary to transmit both sideband. So instead, we are going to use in this example, we are going to use the upper sideband, single sideband suppressed carrier. Compared to this, we can see we use the upper sideband. The lower sideband is from 95 to 100. The upper sideband is from 100 to 105. So we use the upper sideband. We use band pass filter to get this signal. Same thing for the second one. The center frequency is 105. So this one will be 100 to 110. And again, the upper sideband equals 105 to 110. This one is 110 to 115. Another one is 115 to 120. Then we have all these four channels of single sideband suppressed carrier signal. Then we add up together, linear sum, just directly add them together. So the bandwidth will be from 100 to 120. So we transmit these four channels at the same time with this same channel. It's shared in frequency. Then once we receive this signal, what to do this? How to do this? What's next? Band pass filter, right? You band pass filter, you get each one, then use a demodulator to get the baseband, followed by low pass filter to get this one. Okay, questions on this? Everything good? And those are some most recent news. So I don't need to mention this. You can read it by yourself. So they have new techniques that can boost the signal transmission capacity. Next one is the Lienholder, which is the topic of the third lab. You are going to discuss a lot of more details by yourself in the lab. Here, just give you a brief introduction. Return to zero means before the end of the cycle, the signal must return to zero. Transmitter one, for example, this cycle, this one does not return to zero until the end of the cycle. So that's why this is called non-return to zero. If you want to use a return to zero, you need to have a stop somewhere, maybe half, maybe more than half, before the end of the cycle, return to zero. That is return to zero and non-return to zero. Non-return to zero level, this kind of code, we use 0 to represent high, use 1 to represent low. For example, here, this is non-return to zero level. This is 0, 1, 0, 0, 1, 0, 1, 1, so on. And this one, 0, use high to represent, 1 use low to represent. So high, high, low, low. So that's very easy. If you know in the lab, if you know the transmitted signal like this, and you can observe on the oscilloscope the code, then you can determine what kind of code this is. Non-return to zero, inverted. Inverted means if for 1, if 0, there's no transition. And if the data is 1, then there is a transition at the beginning of the interval. Look at this. 0, you just use this. Right? 1, that means we need to have a transition. This is low, so the transition will be to high. Right? So that is why it's high. And this is 0. 0 means no transition, so high, still high. Right? And this one is 0 again. 0 again means no transition, so high, still high. And this one is 1 here. 1 means we have a transition, so from high to low. And next one is 1 again. 1 means have a transition, so from low to high. So we can call this one. This is called non-zero, non-return to zero inverted. We have some multi-level binary, bipolar AMI, all this code. We just discuss those are the benefit properties of the code. And that's very easy to understand. So I suggest you read it by yourself. And we discuss this one here. Can anyone explain this? Why this is called this is bipolar AMI? I want some explanation. Okay, the first one is 1. Sorry, the first one is 0. It's here. While this one is this. Alright, that's AMI. So what is AMI? AMI means 0 is transmitted as no pulse. So 0, no pulse here. And 1 is transmitted as a positive and negative pulses in alternative sign. Right? So the first time 1 which was positive, right? Then this 0, no pulse here. Then the second one is the alternative. So this is positive, then this one must be negative. Right? Then 1 again, this one is negative, the next one will be positive. And 0, nothing. And this is positive, so this one is negative. So that's how we get the AMI code. Again, in the labs, you have the input code and you need to check if this one is true. You can see clearly. Right? Pseudo ternary. The rule is if 1, no line signal, 0 pulses of alternating sign, opposite to this one, right? AMI and PT are opposite. So 0, we use a positive here, and 1 is 0. Then another 0 means we need to use negative. Then another 0 we use positive, and 1, all positive. So this different code have different properties, and we need to choose different code with different applications. So we need to know which one is good for what application. Any questions on this? That's easy, right? The third lab is like this, right? 5-phase techniques use 1 or 2 transitions per bit time, and the property is bytecode code are self-clocking. Self-clocking means from the code itself we can extract the clock. Some code does not have this kind of property. For example, we said use non-return 0, just the ordinary. If we have a lot of ones, what do you get? If we have a lot of ones, we get a high, 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 or high, a straight line. Then if you receive this kind of signal, do you know the clock? You receive a whole line of ones, all zeros. You do not know where the clock is. So the 5-phase, you can automatically, no matter it's 1 or 0 or long ones or long zeros, you can automatically extract the clock here. For this one, 0 means high and low. 1 means low and high. So the 0, high, low, 0, high, low, 0. So you can see from this code, no matter you have a lot of zeros or a lot of ones or 1 zeros interchange, you can find the clock automatically. So this is a biphase. And also, statistically, this signal has no DC component. Because this one, they cancel each other. This one cancel each other. So no DC component. That means all the frequency transmitted will be a high frequency. Why this is good? Why we do not want a DC component in the signal? For example, if you have a DC component in the signal, how are you going to transmit wirelessly? Can you transmit the DC signal wirelessly?
For a short time?
For short term. You mean short range?
Yeah, short range.
Right? But that is not a real DC. You change still, theoretically still change AC. Right? You directly transmit DC. Can you transmit your 3.7 volt of battery wirelessly to somewhere without any DC involved? No way, right? So DC cannot be transmitted wirelessly. If you have, for example, 1, 1, 1, 1 like this, how can you transmit this wirelessly? You cannot. But this one, we don't have any DC component, so this is a perfect, can perfectly transmit it with the wireless channel. Right? So this is called a Manchester code, and another one is called a differential Manchester. Differential Manchester means if 0, then we do not have any transition at the beginning. If 1, then we are going to have a transition at the beginning. Right? Anyone can explain this? Right, so 0, we have a low, high. How we get this? 1 means we have a transition at the beginning. So this is low, high, then 1 means high, low, right? Because we need to have a transition, change. And the next one is 0. 0 means no transition, right? The previous is high, low, then this one still high, low. That means no transition. Right? The next one is 0, means does not change. This is high, low, and this one still high, low. Make sense? Okay, the next one is 1, means we need to have a transition. So this is high, low, and the next one means low, high. Right? Then this one is low, high, and this one means high, low. So we change the transition. Right? So very easy to understand this. And also you need to, in the lab report or in the labs, you need to tell what's the difference between this. Not only from the waveform, what's the benefit, or which one is better for what kind of a situation. Any questions for this? This is the summary for all the code we are going to discuss in the labs. In the third lab, I believe we already finished the second lab, right? PCM code. The lab report is due next time, right? Line code techniques, why there are a lot of researchers doing this? It's called the encoding technique. Why we want to do that? Those are the benefit. We can reduce the channel bandwidth. Proper coding can make the transmission bandwidth as small as possible. And power efficiency, if we do not need to, for example, transmit the DC, then the power may be small, right? To make transmitted power as small as possible, and error detection. Some code automatically have error detection capability, or some even have error correction capability. That means for error detection, if you receive the code, you automatically know if there's an error inside or not. Right? That is very good property. But some even better, right? If you receive the code, you can decide if there's an error inside. If you decided there's an error inside, then you can automatically correct the error. Right? So this is the error correction capability. Favorable power spectrum density, zero DC component for AC coupling in the repeater. Remember when we design amplifiers, between each stage, usually we are going to use a capacitor, right? So that means if you have the code have a DC, if your input has DC component, then you cannot use this kind of amplifier because they cannot be coupled from one stage to the next through the capacitor. If the code has only AC component, then that's perfect. Self-clocking, clocking, we already discussed this. And the data transparency, that means the bit pattern does not affect the accuracy of the timing information. It's very similar to self-clocking. Alright. Another one is, this one is the relationship between the coding and the bit error rate. You can see for the same, for example, probability of error, BER here, like this, and for different coding technique, they have a different requirement for the signal to noise ratio. We can see for this one, here, for the same, for example, 10 to the negative 6. That means we have one bit wrong in every 1 million transmitted. So that bit error rate equals 10 to the negative 6. To obtain this kind of a property, the signal to noise ratio for this kind, now return 0, YFS, PSK, QPSK, the signal to noise ratio must be here, like a 10.5 dB. But for this kind of code, AMI, ASK, FSK, the corresponding signal to noise ratio required will be like this is 10, and this one will be 13.5. So that's the difference is called, that's the difference of 3 dB. This is called coding gain. Right? And different code have different properties for this. Next one is a regenerative repeater used for long distance transmission. Detect the incoming code and regenerate the clean code for retransmission. Advantage over the analog is the analog, for example, you have analog, you have additive noise. Then usually you cannot remove the noise because if the noise is inside the band, then you cannot filter out. Then the quality can only be worse and worse. But for digital, and that's the beauty for digital transmission. Once you receive the code which is getting worse, then you stop your regenerative. In the regenerative repeater, you process, you generate a clean code then for retransmission. Something like you restart. So the property can be, the quality can be much better than analog signal. Incoming code control resonant circuit. Okay, so I believe this one is the diagram for regenerative repeater. So this is the code transmitted up to you. It's getting worse. So this is low, this is high, this is low. Looks like not that perfect. Then you use amplifier and the equalizer and reshape the process and timing clock. All this auxiliary circuit. Then regenerator, you have a decision. You need to decide what is high, what is low. Then recover the clock like this. Okay, now this will be the recovered clean code. This is the output of your regenerator, which is supposed to be equal to the input, but it's with much better quality. Data transmission code, what we discussed so far is only like one dimension. And we have some other two-dimensional code. One-dimensional code we involved before is like, we have others, Morse code. Anyone knows that? A little bit, right? If you are interested in ham radio, club, ham radio, before they need to test the Morse code. But now they don't need to, because less number are using it.
Ham radio club?
Ham radio club, yeah. Amateur radio club.
Where is it, up here?
Yeah, we have one, right? But it looks like not everybody is interested in this. You have cell phones, you can record, but we still have this. In Hattiesburg, we have, in the city, we have very active ham radio club. In USM, we suppose we have one. For like 5-6 years ago, we have some activities, but most recently, we don't. We have the transmitters, we have the receivers, we have the antennas, and we have done some interesting things before we communicate with the other side of the world. And if anyone is still interested, we can discuss later. Alright, so Morse code, baud code, and ASC, everybody knows this, right? And EBCDIC, and that's BCD code, right? The 8421 code, everybody knows this, right? This is just binary, right? The first one represents 1, the second digit, the weight is 2, then 4, then 8. Okay, XS, 3 code, Greek code, right? Then all these are one-dimensional code. And we have some two-dimensional code, that means it must be on the surface. So bar code, everyone knows that, right? Okay, UPC code, postnet, data matrix, and QR code. We are going to discuss several of these. This one is Morse code. They use a different length of signals to represent different letters. Usually they just push the button to do this, but there are a lot of variations. For example, you have a flashlight, right? Flashlight usually have some SOS function. They transmit through Morse code. If you can detect those the light, so the on and off represent something. Right? The thing we want to mention here is, at the beginning, when they designed the Morse code, they want to improve the efficiency. For example, do you know which letter used most in English text?
E.
E. Okay, so now E, look at the E. If you want to transmit E, you only use a short dot. For example, if you want to put letter, you just very short. If you have a lot of E's, this one will save you a lot of time. So that's good. Improve the efficiency. The less frequently used the word from here, which one? Maybe the letters first, okay? Which one if we use the least frequent?
Q.
Probably Y.
Q.
Maybe a J, maybe a Q,
Y.
Y. So the Y, where's Y? Right? Yeah, maybe Y. So the longer ones use the less efficiency, and the shorter ones use very frequent. Right? So that is very easy to understand. Alright. If you have time, right, have a study of this. Sometimes this can save your life, right? Yes or no?
Yeah.
I remember that story. Somebody is in the train, and the train in the front, the bridge is already is down. So there's another train coming in, and he want to avoid the other train. How to do this? No one, because at that old time there's no like cell phone or something. They cannot communicate. One guy knows Morse code. He just push the horns, then transmit the signal. And the other train hear it, then stop. So save a lot of life. So that's sometimes it's good. Right? The next one is baud code, and nothing. I don't know where we still use this, but maybe some like rare applications. That's nothing fancy. This one is data matrix code. this count matrix is consisting of black and white cells or modules arranged in either a square or rectangle pattern. Some are rectangle, some are squares like this, white and black cells. Two solid adjacent borders form this L. The reason for this one is this is called a finder pattern. So if you have, for example, image reading code, want to read this one, you need to know the orientation. And you may want to read it like this or like this. This L give you, you locate which is the correct orientation. So this is called a finder pattern. And two other borders consisting of alternative dark and light cells or modules. This is for timing. So look at this one, black, white, okay, so dark light, all these alternating. So this one give you like the frequency, give you the timing. Right? Like this. How wide is this one? If we don't know this, then we don't know, right? So first we need to read from here. So like the timing is this. So look like this one has a what's that? What?
36.
This is 1, this is 2, right? 3, 4. So this is the length equals 2 in terms of the alternative light and dark. So if you want to write to implement some device to read the code here, then you need to consider all this one. Write everything in the code, then you can read this data matrix code. Common on printed media such as labels and letters are mostly used in North America. The next one is a quick response code, QR code. That's very similar to the last matrix, but this one you can see there's difference. Right? Specific matrix barcode readable by quick response. So the response frequency is supposed to be faster than that. And use barcode readers and camera telephone designed to allow its contents to be decoded at high speed. Consists of black modules arranged in a square pattern and white background. The information encoded may be text, URL, or other data, mostly used in Japan or Europe. Alright, so you have a phone here, right? So everybody now this time you get your phone out. Do you have a phone with you? Right? So you have a QR reader. Right? Can you read this?
For Walmart.
Right? Everyone can try? You have the QR reader in your phone, right? Can you read this matrix?
The projector light gonna have to be a little brighter. So
The projector has?
it needs to be lit.
No. Can you read? Did you see anything?
I can't get it from this. I'm trying actually.
I'm making
We'll see what happens.
Right?
See if I'll actually read it.
I see something, okay? So that's my website. Right? And there are a lot of online programs that let you write the contents of yourself, then they give you this one, you can download it, put it in, and you can put on your shirt or bag. No, somebody read all of it, I know your name, right? Who you are, and like this. So you can do. That's nothing fancy, but that's, at the beginning it's interesting, right? Okay. And this one is the world's first QR code coin. It's Royal Dutch Mint, this one. And also, there's a code here. If you read, they give you the website to the mint. Right? Sources of errors. Right? Line outage. That's nothing fancy. It's very easy to understand. Right? If there's no power, then you get a error. White noise. What is white noise? We call this before. This is called white noise here, but we call this in this class before. What do we call? What noise we discussed in detail. In the test, in the homework, unless you calculate a lot of noise, powers, noise voltage, what noise is that? Thermal noise?
Oh, thermal, yeah.
Yes? Right? Thermal noise is called white noise. Why is it called white noise?
It covers the whole signal when you look at it.
Kind of, not the whole signal, it's the whole spectrum. White noise. What is the spectrum for the light, white light? From all the way low to all the way high, right? The white noise, the thermal noise, the spectrum is also from very low frequency to very high frequency. It's uniform. Right? And so it's very similar to the white light. So that's why it's called, sometimes it's called white noise. If you have a communication system, you always have white noise. Is this true or not?
Yeah.
Can you calculate the power of the noise? What is the power of the noise? N equals you need to memorize something, right?
Input or output?
How to calculate the thermal noise, the power of the thermal noise? Give you a system, give you an amplifier. So K, Boltzmann constant, times okay, now times related to what? Temperature, right? Times T, then the other one, B, okay, perfect. It's the bandwidth. The larger the bandwidth, the larger the thermal noise. The higher the temperature, the higher. It's proportional to temperature and the bandwidth. The temperature need to use unit Kelvin. So for example, the room temperature is suppose that equals 27 Celsius. Suppose. Okay? What number are you going to use in the formula? Some of you get this wrong in the test.
297.
Okay, 297 plus 273, right? Plus your Celsius degree plus 273.15, okay? Plus 273. Impulse noise, that's for sure. For example, if you have thunderstorm here, then boom, okay? So at that time duration, you get all noise. And the crosstalk, because of improper shield and echoes, and sometimes you make a call from your computer, you hear yourself. What happened here?
Your microphone probably.
Your microphone, something wrong. So what's it wrong? What's the reason you hear the echoes of yourself?
The wire.
Huh?
The wire is not always plugged in.
The wire is plugged in is not properly. So that is the obvious reason. But technically, what's the reason?
Probably a line broke or so.
Because of the impedance mismatching. For example, when you design amplifiers, you have stage 1, stage 2, stage 3. All these different stages must, the input impedance, the output impedance must be matched. So for complete signal power transfer. If you have a mismatched frequency impedance, then you are going to have reflections. That gives you echoes. Attenuation or distance, that's for sure, right? For example, from here to California and this long distance, the signal will drop. In 315, we are going to discuss how this drop, quantize the error, but here you only need to know this. Jitters, small variations in the amplitude, frequency, and phase of analog signals. For example, the signals will, if you record the signal will not be like flat. Even for continuous amplitude, like for example, just the sinusoidal function, x equals a times the cosine something. The constant, the amplitude is supposed to be constant, but when you record this, it won't be constant. It will have variations. This one is because of the jitter. Physically, because of what? Why you can have these variations? Looks like a thermal noise. Because we have reflections from the walls, from anywhere. So what you hear from me, the major part is direct transmission, but you also hear something transmitted there and reflected to a ear. Communication channel is the same thing. You are going to receive a lot of reflections, diffractions, and all this. Add up together, this give you jitters. Harmonic distortion. Harmonic distortion means you have a nonlinear device inside your system. We need to have a nonlinear device, right? What device is nonlinear? Resistor.
Oh.
Resistor is linear or nonlinear?
Linear.
Linear, right? Capacitor.
No.
Capacitor is linear. Or inductor is linear. What is nonlinear? We mentioned this. We mentioned this when we do the
Transformers.
okay,
Non-linear versus linear?
nonlinear device. Amplifier. The reason is, but we said a linear amplifier. But the reason is we have a transistors inside. Transistor has diode inside, so something like this. Anyone involved with diode or transistors, they must be nonlinear. So if you have some devices components like that inside, then this is a nonlinear system. Then you are going to have a harmonic distortion. For example, this frequency here equals 60 hertz. 50 hertz, right? 60 hertz. Then you are going to have 120, 180. All these are called harmonic noise or harmonic distortions. Again, when you design the amplifier, you said this is a linear amplifier. In amplifier, you always use transistors. Why you still call it the linear amplifier? Y equals the output equals constant times input. It's the linear. Why? There's a condition for that. That condition is called a small signal approximation. Only when the input is small, the output is approximately linear to the input. So any questions up to so far? Any question on this? All right, now let me ask, how many of you have finished the lab, the second lab? How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're supposed to have 50.
I ain't signed.
You already have group or not? Not, right? So how about I'll let form a group for you. Looks like you have difficulty forming your own group.
I got my group already.
Already got my.
You already have your group,
Yeah, I
right?
got my
Who's in your group?
More important hit? Oh yeah, more important to make that.
Okay, one,
Yeah.
you. Okay, you three. Who's in your group?
Jalen and Nicholas.
Okay. Who's in your group?
Ain't Jay.
You three. Okay, nice. Who's in your group? You and okay. Who's in your group? Okay. There are two more. We have 15, but we have one student. So you will be the group with the other group and see who they are.
There you go.
One is called
Quiz last Tuesday.
Pork is here.
Like on the syllabus.
Jacob Cruz. The other one is called Defia Technical. Technical girl.
I'm pretty sure that. It was my only place. I don't know where.
Way from good sleep early.
I don't know. Only one person know what
So any which group was have started the lab? No one?
I think I heard.
Have started the lab menu. That
I don't know what
means
else.
if I ask you some questions about the lab menu, you can answer. Anyone? No? You know the lab report is still 2 days from today, right? So you haven't started yet.
So my Wednesday?
Yes. 46 hours from now.
You gotta get on it.
Huh? Why you haven't started yet?
Yeah, I know it's gonna take more than 2 days.
You already have the template. Everything in the template will I'll create your report based on the template.
Yeah, I don't know about that.
You need to, I know several groups of you have the team member evaluation. Right? That's perfect. Not all of them. Some group has no. So you're going to get some deduction marks from that part. Right? And so that's a reminder. You need to put everything there. And the log books. Who sent me email said, what is log books? I never done any log books. Some of you said you never done log books.
Who sent them an email?
I do not have too much, okay? Somebody sent me and said, I know nothing about log books. I don't think this is true. Right? Every lab need to have log book. Log book means when you start, you write everything, the raw data. You observe something when you write down, okay? Something weird, you write down. And then you discuss everything. Then you have this raw data, you process, you write your lab report. You need to attach your log books to the lab report. And if you do, for example, like circuit, you write all this, like voltage, current, all this. But for this one, you may say, okay, I need to record that screen, the oscilloscope or something. Then you can take a picture of that. But you need to keep your original picture in case I say, okay, you need to show me your image. So you need, for safety, you'd better put your face in there also. Show me that you did the labs and the result. I'm talking this has the reason, right? You understand the reason, right? No?
I don't understand.
Somebody copied, just borrowed the images from others. So now you understand better, right?
My group don't do that.
Okay, so I didn't say your group, but some groups. Maybe not this year, but so that's possible. So better, you need to show, and also, this is the lab, this is team work. Anybody cannot do by him or herself. You need to do together. And again, better to show three faces together. Does it make sense to everybody? I need to do this, right? Otherwise, somewhere will argue with me. Oh, that is my work. It looks like not, but. Is this good?
Yeah, that's good.
Okay. Any other questions?
Do we get bonus points for like a selfie, like a group selfie?
You got bonus for what?
Hey, y'all take it all day, like
Crazy stuff.
If you don't need to, but you need to show me if I suspect, okay? You need to show me that is your work.
Why he suspect and stuff?
The very straightforward way is you got selfie, okay? That is doing it, right? You can have other methods, right?
just like you would in 316, man. You gotta take a picture of your face on it.
Any other questions? Okay, as we said, we already discussed, not everybody has heard that. We can extend a little bit the lab report. So it's due next week, Wednesday, so we can give you a next...
Wednesday.
No, Wednesday. Next Monday.
Oh, next Monday.
Right? Next Monday. That makes sense? Then the last one is also one time. One time, maybe 2 days, maybe 5 days. Depending on your luckiness. Right? The luck is maybe 5 days or maybe 2 days.
Starting to feel like
Okay, so any other questions? We are going to have a midterm test Monday
Wednesday.
next week.
Wednesday.
We ask for extension.
I'm saying Wednesday.
Yeah, Wednesday would be good.
Monday, you know, we might not be thinking right.
So you need to think right, okay? Because Monday, I cannot extend a long time, right? Because we are going to, we are already at the end of this semester.
Okay.
We have only 2 times, then we are done. That's it. Right?
We're gonna have like a review Wednesday.
Yeah, you can have a review Wednesday.
I'm talking about you gonna review Wednesday, like we're gonna be on the test.
What do you need to review?
Oh yeah, that's a good idea.
Yeah,
That's a good idea right there.
Eh?
Yeah, that's a
You
good
need to
idea.
review?
Yeah.
Okay, I'll give you a review. Eh? But you need to tell me what you want to review.
We're gonna
Nah, you tell us what's on the test.
Okay, before the review, I will ask you questions. What you already know in the class.
I don't know.
Eh? You cannot give me a blank head, right? You need to have something.
Man,
Okay, any other questions?
I don't want to start with you, bro. Just go on in the class.
The homework still Huh? Still today? Okay, nice. I don't know that. You should know. Okay, that's it for today. Now, if you haven't done the lab yet, you go to the lab, to do the lab right now.